Hi, welcome to the video on implementation of bagging and random forest. By the end of this video, you will be able to build a simple bagging model and build a random forest model. Now that we are completely equipped with the fundamentals of the bagging and the random forest, let's now jump forward to implementing them. Before we start working with the notebook, I want you to specially note that you should update to the latest version of sklearn version 0.22 on New Year. We will be using some functionality which is not available in the older version of the sklearn. To download the latest version, run a simple command in your Jupyter notebook, that is pip install -u scikit-learn. This will automatically download the latest version of the scikit-learn in your Jupyter environment. We start by importing the churn prediction simple dataset using pandas. We have been working with this dataset for a while now, so we'll skim through the preprocessing part. In preprocessing, we begin by separating the dependent and the independent variables. Next step is to scale the independent variables, now that we are not scaling the target variable as this is a classification problem. Lastly, we are splitting the data into train and test sets. Note that stratify is equal to y, which means that both test and train will contain the target variable in equal distribution. Also, we are using the random state equal to 101. This ensures that data is split in the same way whenever the random seed equal to 101. This ensures reproducible results. Now that our pre-processing is complete, let's try our hands on the bagging classifier. For any bagging classifier, we will be importing the bagging classifier class from the module sklearn.ensemble as BC. And as always, we will be creating an instance of bagging classifier as a classifier. Now, let's just fit the model over the training set and observe the default parameters of the bagging classifier. In the output, we can all see parameters of the bagging classifier. Let's take a closer look at the most important ones. First is base estimator. This parameter requires a machine learning model which will be used with the bootstrapped data. By default, the base model used is a decision tree. So none here means that decision tree is used. Next parameter is bootstrap. This is obviously the most important aspect of using the bagging technique. It is set as true by default. Next is bootstrapped features. This was originally the characteristic of random forest, but is now available to be used with other algorithms as well. But bootstrapping features really shine when combined with decision trees. For now, we will keep the default value of this parameter, that is false. Next is max samples. This parameter deals with the maximum number of samples that each model should receive. This number is defined as the fraction of the data originally given. Right now we are keeping this as 1 because we want every model to receive the same size of data as original data. We will be exploring this parameter in the hyperparameter tuning phase. Next is n estimator. This specifies the number of estimators, that is, number of models to be built for training over data. One might think that more models are always better, but we'll find out. Next is n jobs. This specifies the number of CPU cores we want to use during the training of bagging classifier. We can enter an integer number corresponding to the number of CPU cores we have. Specifying this as -1 will use all the CPU cores available. But let me warn you, keep a fire extinguisher nearby. Your system is going to turn into an oven if your ensemble model is too heavy. Now that we have covered the parameters, let's try a bagging of logistic regression. For this, we will simply import the logistic regression classifier. And following a similar pattern that we have been for a while, we will create an instance of the bagging classifier and pass the logistic regression class as the base estimator of bagging. Also, we are setting n estimators equal to 150, which means that 150 logistic regression models will be combined to generate predictions. Note that we are setting n jobs equal to -1. This will use all your CPU cores. You should have been warned. Lastly, we will fit the model over the training set and generate predictions. In the classification report of the training and the test sets, we can clearly see that the F1 score over the training and the test set are very low. But bagging was supposed to do a very good job considering the fact that there are 150 models behind these predictions. So what happened? Remember that we are using a linear model and the data we are using has not yet passed the feature transformation and feature engineering. Therefore, each logistic regression model with the bagging is underfitting the data and therefore the result. We would suggest you to perform the feature engineering over the dataset and try the bagging technique again. Now, let's shift our focus to the special case of bagging, which is the random forest. For this, we will import the random forest classifier class from sklearn.ensemble as RFC. Next, we will create an instance of the RFC as a classifier. Note that we are not specifying any parameters as of now, but we will be experimenting with them soon. As always, we will now train the RFC model over the training set. We can clearly see all the default parameters of the random forest classifier here. Note that besides the parameters of the bagging technique, we have all the parameters of the decision tree classifier. Also note that there is no feature sampling parameter here. This is because feature sampling is compulsory for the random forest. On predicting the values for training and the test set and generating the classification report, we can see that there is a significant overfitting on training set. On the test set, we are getting a performance of 0.55 F1 score. This is a natural expectation when it comes to any algorithm based on unconstrained decision trees, but this is still much better than the performance that we had when we were using the individual decision tree, which gave us a performance of 0.45 F1 score. So we can say that random forest gives a slight edge over an individual tree by default. In the next video, we will understand how the bagging parameters affect the machine learning models. See you there.